So let's get started today. We're going to be talking about something called the rational root theorem. And this is going to help us determine factors if we're not given a factor. Like last week we looked at one problem where we weren't given a factor and we were able to graph it. Historically in AGS3, what I've done is if we haven't had access to Desmos or graphing calculators, we need this method in order to find factors. All right, but this year, because we're doing this remote learning, I've allowed the use of Desmos and graphing calculators, but you'll still need to know how to find the factors just in case. Like, it's good to know how to do it by hand. So we're gonna start by focusing on the leading coefficient and the constant term, all right, for the rational roots. All right, so if f of x, and this is this whole expression for a polynomial function, which we kind of broke down a couple class periods ago, if it has, we'll say, if it has integer coefficients, all right, then every rational zero of f, which is just the function, has the following form. Every single one is going to look like this, and we're going to talk about it. It's going to be like this. P divided by Q are kind of these placeholders. And we'll write down the top line as the factors of the constant term. A sub 0. The bottom line is the factors of the leading coefficient. A sub n. So again, we'll highlight A sub n there, and we'll highlight A sub 0 there. So what this basically means is we can identify possible rational zeros by looking at the very first coefficient and the very last coefficient and then dividing the two. That's what this means. Okay. And just refresher, what does rational mean? Because it says then every rational zero. Well, rational means a number that can be expressed as a fraction. Because sometimes we'll have irrational zeros, and those ones would be something when we use the quadratic formula to solve for a missing zero, something like that. All right. So looking at this this first example here, if we say f of x equals x to the fourth plus stuff plus 15, what we'd be concerned about is the first and the last term. Notice that there's these dots. So there's going to be a whole bunch of other stuff in the middle. But when we're using the rational root theorem, the best part is we don't need to worry about any of that. We're just worried about what's in the middle, or what's on the outside. It's the leading coefficient and the constant term at the very end. All right. So we know factored form, because this is x to the fourth, it's going to be factor form is going to be x plus a, x plus b, x plus c, x plus d. There's going to be 4 x's, which is good because it's a 4th degree polynomial. So that's what factored form should look like. What the rational root theorem is saying is that a, b, c, and d have to multiply together to get us positive 15, because that's what the number was up here. A, B, C, and D have to multiply to get us positive 15. Another way of saying that is that A, B, C, and D are factors of 15. And 15 is the constant term, A sub naught, from the general form at the top of the page. So what this means then is we can just say, what are the factors of 15? And if we can list those factors, for example, like I know 1 and 15 are factors of 15. What other factors of 15 are there? Numbers that multiply to get us 15.
3 and 5.
Exactly, 3 and 5. So that would be it. So the only tricky part is I could say positive 1 times positive 15 equals positive 15. Or I could also say negative 1 times negative 15 equals positive 15. So I have to consider both positive and negative factors. Same thing happens with 3 and 5, right? I could say, hey, negative 3 times negative 5 equals positive 15. Or positive 3 times positive 5 equals positive 15. So in reality, there are 8 possible factors of 15. If we consider the positive and the negative answers. 8 possible factors of positive 15. Okay? And then there's a lot of potential factored forms we could write down. A lot. So what we're going to do is I'm just going to write down 4 potential ones. But I'm just saying 4 potential because you could list a lot more potential forms than just 4. For example, we could say this could be x plus 1, x minus 1, x plus 1, and x minus 15. And as long as those 4 numbers multiply to get us positive 15, then that's a potential factored form. Okay? As long as we don't know what the middle stuff is. Okay? So that's plus 1 minus 1 plus 1 minus 15. That would equal positive 15. Another possible representation could be x minus 3, x plus 5. Negative 3 times positive 5 is negative 15. So I need another negative in there. That gives us a positive 15. And then multiply by positive 1. That gives us a positive 15. Okay, so that's another possible representation. We could start with just like x plus 15 and then just say x plus 1 plus 1 plus 1. There's a possible representation. So there's a lot of possible representations out there. Maybe x plus 5 and x plus 3 and then x minus 1, x minus 1. A lot of different ways you could write this up. This is just 4 examples, so there's way more than 4. I just made these numbers up just as long as they add to, or they multiply to positive 15. You can do any 4 numbers you want, as long as they multiply to positive 15, and they're all integers. Okay? All right, so it is possible as well to have non-rational roots, which says that the zeros could have just as easily been like plus or minus root 3, plus or minus root 5, plus or minus root 15. And it's important to note that each of these roots, if they did appear, they'd appear in pairs. So if you have a positive square root of 3, you're going to have a negative square root of 3 as well. And these are called conjugate pairs. All right, and that it actually opens up even more possible zeros, but they'd be non-rational. If I were just asking for rational zeros, you're good with this list up here for rational zeros. But another example here is, let's say if I gave you a problem that started with x to the 4th and ended with positive 15, and you were factoring it, and you got this part done right here. This is factored form, but you would say, okay, I've got 1x, 2x, 3, and 4x's. I want to break down that x squared minus 3, which is a difference of squares. We've talked about that a little bit. So difference of squares means I can square root that last term. And I can write it as x plus the square root of 3 and x minus the square root of 3. That's what I mean by conjugate pairs. There has to be a plus square root of 3 and a minus square root of 3 whenever we have a radical introduced as a non-rational root. Because now you get negative 5 times positive 1 is negative 5. And then you would have positive root 3 times negative root 3. That becomes a negative root 9, which is negative 3. And then you get a negative 9, or negative 3 times negative 5. That gets you a positive 15 when they all multiply together again. Kind of weird, but non-rational roots are a possibility as well. Okay? So what I want you guys to do right now is try to practice these two problems. Look at these two problems and determine how many possible rational zeros there are. So you don't need to worry about radicals, just possible rational zeros right now. See if you can list all the possible ones, which is basically what we did right up here. So look at the first number, the last number, and list the possible rational zeros. Take a second to do that now, if you know what I'm talking about. If you don't know what I'm talking about, just hang out. We'll go over it in just a second. All right, so what I've done so far is I just highlighted the front to say, hey, there's actually a number 1 right here that we don't see. So there's a 1. And then we're going to worry about that a little bit more in a minute here. But for right now, we just need to look at the negative 6 and say, what are the possible factors of negative 6? Well, you could do plus or minus 1 and plus or minus 6. And then plus or minus 2 and plus or minus 3. That would be your possible rational zeros. Just all the factors of negative 6. All right. With 18, we would do something similar and say plus or minus 1 and plus or minus 18, 2 and 9, 3 and 6, and then 4 doesn't go in, 5 doesn't go in, so that's your list. So this first example has 8 possible rational zeros. When I ask you to list possible rational zeros, that's what I want, just that list. Doesn't mean that they are the zeros, it just means they're the possible ones. How many possible rational zeros are there in the second one here, if we counted them up?
Oh.
12, exactly. So there's 12 possible rational zeros in the second one, right? Everyone's got a plus or minus. It doesn't matter whether the sign's positive or negative, it's always going to be plus or minus when you're writing down the possible rational zeros. All right. All right, so now when we, what we would technically do with all of these is at the very top here, it says we're going to do the factors of the constant term divided by the factors of the leading coefficient. But in these examples so far, the leading coefficient's just been 1. So technically this would be like, oh, divided by 1, divided by 1, divided by 1, divided by 1. Which anything divided by 1 is just going to be itself. So we don't need to write divided by 1 here. But we are going to look at an example here in a minute where the leading coefficient is not 1. Okay, so that's kind of what we're moving towards. But first, let's do a couple of examples, just so we get used to this. One thing we want to note is that we don't want any fractions when we're writing our function in factored form. So we start with this f of x equals x cubed minus 8x squared plus 11x plus 20. And we want to write it in factored form, which is what we did last class. That was like our homework assignment. But we're not given any factors. So what I want to do is I want to list all the possible zeros first. So it's a positive 20 there and a positive 1 here. So I'm going to go and list them. 1, 2, 4, 5, 10, 20. Because 1 and 20, 2 and 10, 4 and 5. So there's 12 possible zeros. And the way we can use this information is we can say, okay, well, one of the zeros, let's just start with positive 1 and see, is this actually a 0? We're going to prove it algebraically. And we're just going to take the coefficients and we're going to do some synthetic division here because that's faster than polynomial long division. And if positive 1 is a 0, then I should get a remainder of 0 right now at the end. This is how we check them. So in a normal school year, if we were in person and I were giving you an assessment on this topic, I would ask you, hey, go ahead and plug in, start with 1, and see if when you divide it, if you end up getting a remainder of 0. And sure, when we do this problem, we end up getting a remainder of 24. So that tells us positive 1 is not a rational 0. So there are 12 possible rational zeros. What's the most that's going to actually work for this function? How many factors are we going to find? Like if we wrote this in factored form, how many sets of parentheses would there be if it's a third degree polynomial? It's kind of a weird way to ask that question. But it'd be like x plus or minus something, x plus or minus something else. How many sets of parentheses would there be if it's a third degree polynomial? There would be 3 total, right? 3 separate x's, 3 sets of parentheses. So there are 12 possible rational zeros. There are only going to be 3 real zeros out of these 12. So that means more often than not, we're not going to be correct when we try these. Okay. That's the bummer about this. But we'll try another one. We'll try negative 1. And we'll just keep working through the list. So we know positive 1 didn't work, but we'll try a negative 1 next. Usually a 1 or a negative 1 ends up working, which is kind of nice for us. Usually one of those works. This gives us a negative 9, positive 9. That gives us a 20, negative 20. There it is, 0. Perfect. So remember, this right here is the 0, x equals negative 1. So if I wanted to write that in factored form, I'd have to add 1 to both sides. I'd get x plus 1 equals 0. So x plus 1 is a factor. And then the result is going to be, the result factored form so far is going to be x squared minus 9x plus 20. And then I want to factor the second part. And I could keep guessing and checking, or I could go ahead and say, oh, why don't I just factor this one because I know how to factor quadratic functions. And this will be a lot easier than guessing and checking with 10 more possible zeros and only 2 of them work. So I see factors of 20 that I have to add to negative 9x. I'm going to say negative 5 and negative 4. That's going to give us a negative 4x and a negative 5x. And there it is. There's a x minus 5, x minus 4. So our final factored form for this problem then would be, the first one we found was x plus 1. And then the nice thing is these are already written in factored form for us, x minus 4 and x minus 5. All right, and there's our factored form. That's how we use the rational root theorem. We've identified possible zeros. There's 12 of them, but only at most 3 of them will be real zeros. All right, it's possible to have less than 3 real zeros, but at most 3. And in this case, we had all 3 real zeros. Hopefully that makes a little bit of sense. Looking at one more problem here. This one ends with a negative 18. It's another third degree polynomial. So it says find all of the zeros of this one. So first we'll start by listing the possible rational zeros, which we already had that list above. So I'm just going to copy that exact same list down. And again, it's 12 possible real zeros here. And I'd want to start by saying, let's check 1 again. I always start with the easy numbers. You can start with any number you want, but I think 1 and negative 1 are the easiest ones to check, and usually one of them ends up working. Usually, but not always. Oops, that's going to be a positive 1, negative 1, and then negative 1, negative 22, negative 22, negative 40. So positive 1 didn't work. But then I could try negative 1, and I just start over with the division. And when I plug in negative 1, I end up getting, there it is, a 0 at the end. That's perfect. So after my first round of factoring, the negative 1, remember, is that x plus 1 factor. And my result of the division was x squared minus 3x minus 18. I think what can make these problems really, really tricky is if we haven't mastered synthetic division yet, and we haven't mastered rewriting factored form from synthetic division, that could make this really tricky, because now we're putting everything together. That's what this last 2 days is going to be, putting it all together to come up with a way to factor higher degree polynomial functions. So that can be really difficult for people. So I've got this first factored form written down, and then I can go ahead and factor the second result, x squared minus 3x minus 18. So I get x difference of 3, so I'm guessing x minus 6 and x plus 3. That gives us a positive 3x and a minus 6x. That gives us a negative 3x in the middle. Perfect. So my factored form would technically be x plus 1 times x plus 3 times x minus 6. But this problem's not asking me to find the factored form. This one's asking me to find all the zeros. So remember that would be x equals, the first one was negative 1. And if I did x plus 3 equals 0, subtract 3 from both sides, I'd get x equals negative 3, and then I get x equals positive 6 would be my third one. So that would be factored form here. Okay, that's what this particular example looks like. Hopefully that makes sense. That's not too difficult for us. All right. Now we're going to look at another quick example here. I'm sorry, so many examples today, trying to get through it all. What happens when the leading coefficient is not 1? That's what we're looking at next. So if the leading coefficient is something like a 2, that's going to change things a little bit, but we're still going to be focused on the last term as well, in this case, negative 12. All right, and what the 2 means, if we have that, is we're going to have like some question marks up here with the x's. And one of these, it doesn't matter which one, has to be a 2. Right now it doesn't matter which one, but. So one of these numbers has to be a 2. And the others will all be 1. It follows the same rule as the constant term, where all those leading numbers have to multiply together to get us a result of 2. So one of them will be 2, the rest will all be 1. And then as before, A, B, C, and D are going to multiply together to get us negative 12. Okay. So then it says here, potential zeros for f of x will come from the solutions to one of the following equations. It could be like x plus a equals 0, or 2x plus a equals 0, or x plus b equals 0, or 2x plus b equals 0, or x plus c equals 0, or 2x plus c equals 0, or x plus d equals 0, or 2x plus d equals 0. So there's a lot of possibilities now. That's why it's tougher when there's a leading coefficient. But we can follow the same steps as before, where we say, let's find first, list all the possible integer factors of negative 12. Integer factors of negative 12, we're going to have 1 and 12 plus or minus. We could have 2 and 6 plus or minus. And we could have 3 and 4 plus or minus. That's all the possible factors of 12. Those are the potential zeros. And then what happens is if we divide all of these values by 2, those are the factors of an, because it's just 2, or it's 1 and 2. I should say 1 and 2, but yeah. 1 and 2. Then this gives us a longer list of potential zeros. So what happens is if we listed all the potential zeros, we'd start by saying plus or minus 1, 2, 3, 4, 6, and 12. This is like what we did before. And then what we have to do is we have to say plus or minus 1 divided by 2, plus or minus 2 divided by 2, plus or minus 3 divided by 2, plus or minus 4 divided by 2, plus or minus 6 divided by 2, plus or minus 12 divided by 2. That adds a lot. Because technically, the whole idea is that we started at the very beginning of the day saying this P over Q. Well, P is all of the red terms, and Q would be, yeah, let's do this a little differently. We'll say P, and Q would be the yellow numbers. And technically all of these are divided by 1, but we don't need to write divided by 1, because anything divided by 1 is just that number, okay? But when we look at the other list, hopefully we notice something. What is 2 divided by 2? For example, over here, what is 2 divided by 2?
One.
Yeah, it's just 1. We already have 1 written down over here, so this one's a repeat. We don't need to write that one again. Like, we don't have a 1/2 yet, so that's a new one. We don't have a 3/2 yet, so that's a new one. 4/2, 4 divided by 2 is 2. That's a repeat. 6 divided by 2 is 3. That's a repeat. 12 divided by 2 is 6. That's a repeat. So we can technically cross all those ones out. We already have 2, 3, and 6 written down. So we're adding 1, 2, 3, 4 more potential zeros. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 potential zeros here. But that's a heck of a lot better than crossing out these other 8 and making it 24 potential zeros. But we have 16 here because of all those repeats. But that's how this works with the leading coefficient instead. All right. So this next example here says find all the zeros. On an assessment, even if I don't ask you to, what I want you guys to do is list the potential zeros first, just like what we've been doing here. So for example, this problem here, we'll start with the 15 and say plus or minus 1 and plus or minus 15, and then 3 and 5. So there's 8 potential zeros. And then we're going to divide all those numbers by 2. I would say let's do the 2 next. So 1/2, 3/2, 5/2, 15 halves. And thankfully it's just a 2 that's the first number, because if it was like a 6 that's the first number, we have to do all the factors of 6. So you'd have to divide by 1, 2, 3, and 6. So thankfully it's just a 2. We're just dividing by 1 and 2. All right. In example B, we'll start by listing all the possible zeros as well. There's a positive 6 and a positive 3. So we'll start by listing the possible factors of 6, 1 and 6, 2 and 3, and then the possible zeros of those divided by 3. 1/3, 2/3, 3/3, 6/3. 3/3 is 1, that's a repeat. 6/3 is 2, that's a repeat. But 1/3 and 2/3 are not repeats. All right, so that gives us all of our possible zeros there. And now we can go ahead and see if we can figure out what our real zeros are. So on this first example A, I'll start by dividing by 1. You just kind of have to work your way through the list. All right, we do our division. Turns out we get a 0 right here on the first one, which is perfect. That means 1 is a 0. Awesome. So right off the bat, I found my first 0. I'm still left with 2x squared minus x minus 15. So I would need to try a box method on that. I know the possible factors of 2x are 2x and x. And then negative 15, that could be a 5 and a 3. It could be a 1 and a 15. We've talked about that. There's a lot of ways to factor that number. So I'm guessing here that we'll start with like a negative 3 here, because that gives us a negative 6x there. And if we did a positive 5 there, that's going to give us a positive 5x. I got lucky because that one ends up working. So there's my factored form. It's going to be x minus 1, x minus 3, 2x plus 5. That would be our factored form, but this one's not asking for factored form. It's asking us to find all the zeros. And this is the last important thing I want to mention today. When we find the zeros, we'll say the first one was 1. We know x equals 1 is one of the zeros. Let's go and clean this up a little. X equals 1. Second one, if we do x minus 3, we add 3 to both sides, and we get x equals 3. And then the last one, that 2x plus 5 equals 0. We subtract 5 from both sides. 2x equals negative 5. Divide both sides by 2, and we get x equals negative 5 halves. There it is. And that was one of our possible zeros, which is good. That checks out. So this is one important thing I wanted to mention was we talked about no possible factored form, no fractions when we were in factored form. I mentioned that before. And what I mean by that is, like, if I listed the zeros like this for you and you had to turn it back into factored form, what some students do is they'll see x equals negative 5 halves, and they'll add 5 halves to both sides and get x plus 5 halves and try and write that as a factor. So if you had factored form here, you'd say x minus 1, x minus 3, x plus 5 halves. That's not an okay factored form. You want to write it as 2x plus 5 instead, integer values. So that goes back up to the note I had here. So no fractions in factored form. So that's what I meant when I said no fractions in factored form. I just didn't get to show you an example of that yet. So that's what I mean by that part right there. So you don't want to end up with this x plus 5 halves. What you do is multiply both sides by 2 first, and then add 5, and you'll get that 2x plus 5, if you ever have to undo a 0 with a fraction in it. All right? Yes, we are dividing by 2 and 3 because that's the leading coefficient. Exactly. All right, last example today, example B here. find the possible rational zeros. We've got them listed. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible rational zeros. And then we'll start by checking this one. This time we should have 5 terms, and we do. That's perfect. 3, negative 5, negative 17, 13, and 6. And that means because it's a 4th degree polynomial, we should have 4 possible zeros out of these 12. Negative 19. Oops, that's jumping ahead of myself. Negative 19, negative 6. Perfect. So we got a rational zero right off the bat. X equals 1 is definitely a 0. So that means after the first go at it, we factored x minus 1 out, but we're still left with 3x cubed minus 2x squared minus 19x minus 6. So unfortunately, we don't have enough to do factoring method yet. But what we can do is we can plug in more zeros here, and I can keep going through the list. Like there's 11 more zeros to try, and only 3 of them are going to work. So instead of going through that list, here's where I can be smart a little bit, because we have a tool this year that we normally wouldn't have on assessments. But that's the idea for the last problem here.